So now, working with quadratic forms, we have built up a reason to work with symmetric matrices. And one of the most interesting ways that we have found until now to work with symmetric matrices is using diagonalization. So obviously these two topics are connected, and we're going to look at diagonalization of quadratic forms. As we have seen, we can go from a quadratic form that is x inner product ax to a quadratic form x tilde inner product a tilde x tilde. If we want to work with an easier quadratic form, then we would like a tilde to be easier to work with than a. In particular, well, we can remember the spectrum theorem that says that if A is symmetric, then we can construct a matrix P and a matrix D such that A is equal to P transpose dP, where P is built out of the normalized eigenvectors and D is the diagonal matrix with only eigenvalues on the diagonal. So we have done a change of variables. We want to go from A to A tilde. A is symmetric. Then we want to build A tilde to be diagonal. We want to choose the change of variables in such a way that A tilde is diagonal. What it means is that we can make a change of variables that always eliminate the cross terms. So if we go from a quadratic form that is a small a x squared plus 2bxy plus cy squared, we can choose new variables in your xy plane. We are going to choose x tilde and y tilde, and this same quadratic form is now a quadratic form with no cross terms in x tilde and y tilde. So it's a quadratic form with a tilde x tilde squared plus b tilde y tilde squared. No cross terms. So complete independence between x and y. Looking at second order linear PDEs, how do they connect to the quadratic forms? Well, we want to think about them as a sum between aij and delta squared over delta xi, delta xj. I and j are going through 1 to n. We are again using the Einstein convention sum to summing through every repeated index. In this case, we have I and j being repeated. So we are representing our linear operator L in this form as a sum, finite sum, over I and j of aij delta squared over delta xi delta xj. In 2 dimensions, we only have 3 terms, so we can represent L as the inner product of delta over delta x, delta over delta y, and a matrix A, B, B, C times the same vector delta over delta x, delta over delta y. So we can represent this matrix A being the representation of our aij's, and we can always choose this matrix to be symmetric. So we can use a change of variables to diagonalize L by going from x to x tilde equals m times x. Now by chain rule, if you're taking the derivative with respect to delta xi, then it's the same thing as taking the derivative of delta x tilde j over delta xi times delta over delta x tilde j. It's much easier to have it written than actually saying it aloud. And remember, about the Einstein conventions, there is a sum over the coefficients, over the indices j in this term. So you're really making a sum, checking every single x tilde, taking the derivative with respect to xi, and keeping delta over delta x tilde j. We can use this chain rule by considering x tilde as a function of x. And if you are careful with all the indices, this means that the vector delta over delta x1, delta over delta x2, and so forth, then I'm gonna just notate as delta over delta x vector, is equal to m transpose delta over delta x tilde, where that is also a vector itself. Then we look at our linear operator written as an inner product, and we replace delta over delta x by m transpose delta over delta x tilde. We can move m transpose from the left to the right by canceling the transposed. So now we have a new representation of our linear differential operator, delta, that is an inner product between delta over delta x tilde and m times a times m transpose delta over delta x tilde. And this product, we can choose m to be a matrix with eigenvectors of A to make m times A times m transpose a diagonal matrix. And we can do that because we know that A is symmetric and we know all the nice properties that A has. Take-home message: if you're applying the correct change of variables, you get rid of the cross-derivative terms in a linear second-order PDE. So by change of variables, we can go to writing the differential operator L as an inner product between delta delta x tilde and A tilde delta delta x tilde, where A tilde is diagonal. That means that you can actually write L as a finite sum of second-order derivatives with respect to xi times lambda I, where lambda i's are the eigenvalues of A tilde. Can we use this new way of representing our differential operator with respect to eigenvalues as a way to classify PDEs? Yes, we can, and we're going to be talking about this. We have constructed a way to go from any linear second-order PDE to a diagonal second-order PDE, a diagonal operator. By diagonal, I mean that it's the inner product between delta over delta x tilde and a diagonal matrix D times delta over delta x tilde. So now we have L only depending on the eigenvalues of A. And we can have three cases of eigenvalues. We can either have all the eigenvalues being positive or all the eigenvalues being negatives, and in which case we talk about elliptic PDE. We can have at least one eigenvalue being exactly equal to 0, in which case we're talking about parabolic PDE. And the third case is we have some positive eigenvalues and some negative eigenvalues, and then we talk about hyperbolic. Here you can see why we can talk in the 2D case, we can talk about the determinant of the matrix instead of the eigenvalues, because there is a one-to-one correspondence. In general, on higher dimensions, we actually have to go to eigenvalues to talk about the classification of PDEs. Therefore, we need the information given by diagonalization to actually distinguish between elliptic, parabolic, and hyperbolic. Let's look at an example of a change of variables, maybe making it a bit more practical. So we have a two-dimensional, second-order, linear differential operator. We call it L, and we represent it as the inner product between delta over delta x, delta over delta y, and the matrix A, B, B, C times delta over delta x, delta over delta y. We apply a change of variables, so we want to construct x tilde and y tilde equals the matrix M composed by m11, m12, m21, m22 times x and y. Then we can represent the different partial derivatives of u as partial derivatives with respect to the new variables that we have just introduced. So delta over delta x u is equal to a differential operator applied to u, where the differential operator is in two blocks, delta x tilde over delta x times delta over delta x tilde, and delta y tilde over delta x times delta over delta y tilde. This is the application of the chain rule. And the same we can do when we're looking at the partial derivative of u with respect to y. But now that we have explicitly determined the matrix M, we can replace these terms because we know them. X tilde is just m11x times m12y, so we can replace the various elements. You notice that in the derivative with respect to x of u, we have the first column of m, and in derivative with respect to y of u, we have the second column of m. Makes sense, because when you're doing the matrix product, well, you're going to multiply the first column by x and the second column by y. So we retrieve that when we are doing the vector delta x over delta x, delta over delta y, that is equal to m transpose times the vector delta over delta x tilde, delta over delta x, delta over delta y tilde. So we do the same steps as before, and we can write the second order linear differential operator L as this operator with derivatives with respect to x tilde and y tilde, and a matrix in the center that is m times a, b, b, c times m tilde, m transposed. If we choose m being equal to v1 and v2, then this product is diagonal. So by the change of variable in which x tilde is equal to v1 and v2x, then we can rewrite L applied to u as lambda 1 delta over delta x tilde plus lambda 2 delta over delta y tilde applied to u instead of to x, instead of all derivatives with respect to x. So now we can have a classification with respect to the signs of lambda 1 and lambda 2.